This topic is going to be about free energy change. We won't be talking about all of this concept. When you are reading the textbook, focus on what I cover in the recorded lecture. You are free to read more, but you will be tested on this part. We will be covering free energy, stability, and equilibrium, and how this relates to metabolism. Molecules and mixtures tend to move from an state of high potential energy to one of lower potential energy. To use the diving from the platform example, molecules don't tend to hang out on top of the platform. Their friends down below are making fun of them until they jump. Well, molecules don't really tease each other, but it can help you understand what is going on. Diffusion is an example of moving from a state of high potential energy to one of lower potential energy. If I dropped a sugar cube into a glass of water, the sugar molecules begin to dissolve as they form hydrogen bonds with the water. I told you you'd need the information from chapter 2 through 4. The sugar and the water molecules, both in a liquid state now, are bumping into each other randomly. The sugar molecules eventually mix equally with the water molecules. We call this process diffusion, and we say this well-mixed solution is at equilibrium. It can't go back to having more sugar in one area than in another. There is energy in this movement from a concentrated state to a well-mixed state. This energy can be used by the cell. Molecules that have greater energy potential stored in their chemical bonds tend to be less stable. They will spontaneously break apart, releasing energy as they do. Once the molecule has broken into two or more parts, the parts have less energy than the starting molecule or reactant. It's like the guy on the diving platform. Once the molecule breaks its covalent bonds and falls into the molecules with less energy in their bonds, these resulting molecules or products have less potential energy to do the work of the cell. We often use graphs to show this release of energy or storing of energy. We measure the amount of free energy on this axis in the process of the reaction, or time, on this axis. In this graph, the starting reactants have more energy stored in their bonds than the products do afterwards. Here's another example to help you understand this rather abstract concept. Let's say this is my bank account before a spending spree. This is my bank account after the spending spree. After the spending spree, I now have less free money to pay bills than I had before the spending spree. Bringing it back to the molecules, the free energy is kind of like money. Once the money is spent, or the energy released, you can't get it back. We call this reaction, one that releases energy, an exergonic reaction. To go back to metabolism, catabolic reactions are also exergonic reactions. In this graph, the reactants have less energy than the products. The products have more potential energy than the reactants. To use my money example, after my spending spree, I have to work to put more money into my checking or savings account. Afterwards, I have more potential to pay bills and buy stuff. Going back to molecules, I have to use energy to raise the molecules to a higher state of potential energy, kind of like me working away at my job. These reactions are called androgonic reactions. To connect this term to metabolism, anabolic reactions are also androgonic reactions. Whew, that was a tough concept. Don't worry if you don't understand it at first. We will be talking about these concepts with specific examples, which always helps. Also, the in-class activities should help. Make sure to write down anything you want to ask me about in the lecture question and answer session.